All right, so I think we're passing around some of the outlines for the course. My battery might last is an hour and a half or so, so I will see if I have my charger. If not, we'll finish a little bit early. All right, but I think we will take a break and maybe I can get my charger. All right, so let me just start then. So this is the electrochemistry class. We have more than 40 students in the class. So there was a limitation in the number of students before because we had a different classroom. So that's why I was not giving more PTEs. Now we have a bigger room. All right. So we will generate some more PTEs. If you're in material science, then it should be fine. We can actually give you a PTE. If you're enrolling for the electrochemistry class, we're just making some more, all right? So just be patient and please send me an email at 4 with your UID number. So your name and your UID number, and then I will generate a PTE for you, okay? But don't send it now because then I will check after, all right? So we have two TAs. We have Shruti. She was here a little bit ago, and Arjun. So Arjun, I don't know if you know. So Arjun was an undergrad here at UCLA, so he took this class last year. So he knows the material and everything, right? Shruti, I think she will come in a little bit. Shruti also took this class last year. So both of them are familiar with the book, with the content and everything. All right, so there are some students that have a background in material science. Other students have a background in chemical engineering. This year, there are a few students, I think, from chemistry. And there are different reasons why you guys have taken electrochemical processes. I can tell you a little bit about myself, and then I would like you guys to tell me a little bit very quickly about yourselves, which department you are, what year, and if you have any experience in electrochemical processes and maybe why you're taking it. The slides are already posted in CCLE, all right? So you can actually have access to the slides from today and on Wednesday as well. All right, so I'm a chemical engineer. I did my undergrad, master's, and PhD in chemical engineering. I studied chemical engineering because I had an interest in fermentation processes. Now I'm working something very different, right? I started working in heterogeneous catalysis during my undergrad. I also was an intern at BASF in Switzerland in the plant support group. And currently my interest is in electrochemistry and the use of electricity to drive catalytic processes. And so maybe we can go around and maybe just, if you can tell us just a little bit your name. So why is this important? Because eventually you will have to submit a project report, okay? The grad students, not the undergrads. So I would like you guys to know a little bit about each other, all right? So if you can tell me your name, what year you are, which program, and okay, so why electrochemical?
My name is Wamdi, but you can call me Abdul. This is my first year as a master's degree student in chemical engineering. I'll be working with this students. I've been working as a process engineer or chemical engineer or oil and gas industry for 6 years. And I was sponsored by them to get my master's degree. Honestly speaking, I was advised to take a course like this. I'm not sure what exactly is going to be with this class, but I'm sure that it will be very helpful in my project.
Okay, thank you.
I'm Steven. I'm a second year master's student under Dr. Nabi. I did chemical engineering here.
These are different. There is a different, there should be, I printed 40, so there should be some copies around maybe of the syllabus.
Are they already on the table?
They are being passed around, so maybe there is a few there. I think, or there are, I think, yeah, they're moving. Okay, sorry, Steven.
Okay.
Yeah.
So I'm Steven. I'm a second year master's student at UCLA. I was here for my undergrad as well, so I did my project with you in 108. And I'm with Dr. Nabi doing kind of like molecular biotechnology kind of stuff and kind of medical devices. And I want to take this class because I wanted to get an elective done and learn more about different parts of chemical engineering that I didn't get to do in undergrad.
Okay, thank you, Steven. So Shruti is our TA as well. So she took the class last year. So if you want to stand in this way. Shruti and Arjun will be the TAs. Go ahead, Shruti.
And so I'm Shruti, I'm a second year master's student at Professor Carlos is my PI, and I work on electrochemical systems for CO2 reduction. I did this class last year, super fun, super interesting, get to learn a lot of new things. So yeah, you'll have fun.
Thanks.
So, yeah, I'm Shruti. So I'm a first year graduate student joining for my master's degree here. And I'm very much interested, previously I had worked a bit on fuel cells and reduction of carbon dioxide. And I'm very keen to learn about the technical aspects involved in electrochemical reactions and what are the different scientific terms which are behind it, how its working principles and so on. And I think this would be a great theoretical start for that.
Oh.
And that's why I'm very interested in.
Thank you, Shruti.
I'm James. I'm a first year PhD student. I'm in Carlos's lab, so it's kind of important to take this class. But I also did some chemistry stuff, research in my undergrad as well. It was just for a different application. But yeah, I'd say this class is pretty important.
Hi, I'm Arjun. I'm your other TA. I'm a first year PhD student, also in Professor Carl's lab. I took this class last year because I was primarily interested in electrochemistry and also generally energy.
Hi, I'm Cameron. I'm a first year PhD student in civil engineering materials. And I work with the Institute of Carbon Management. So electrochemistry is very important for that. And there are different processes that have sea change and cost. So I can learn more about that.
Okay.
Hi, I'm Harshita. I'm a first year graduate student doing masters with the chemical engineering department as well. And I'm taking this class just to get a more in-depth knowledge about electrochemistry.
Hi, I'm Emily. I'm taking part in the Masters of Engineering program in Green Energy Systems. I have not taken an electrochemical processes class or have dealt with electrochemistry, but my background is primarily in physics and chemistry and was advised by Dr. Yang that I would need this class very much.
Hi, I'm Kind. I'm a master's student in Green Energy Systems program. My undergrad degree is in aerospace engineering. And I'm interested to learn about fuel cells.
Hi, I'm Rick. I'm also in the Green Energy Systems focus of the Master of Engineering program. My background is electrical engineering, so I'm really interested to see where electrochemistry comes in, what I can make of it.
I'm Steve, a second year master student from Material Engineering Department. I think with this class is because I want to know some stuff during my summer internship with they do something electrocatalysis and I want to know more.
My name is Yi Wang. I am a PhD student of material science and engineering, and I really love the electrochemical process. And I have done this field for 4 years during my undergraduate research. And my future research direction is the electro catalyzer, the PMWE, and the water oxidation. So it is really important and necessary for me to choose and learn this lesson.
All right. Okay.
Hello, I'm Pranav, second year master's student in material science. Currently, my research focuses on hydrogen fuel cells, so electrochemistry is pretty imperative for that, and I would want to deepen my understanding.
Hi, my name is Ajay. I'm a second year grad student at the material science department here. My undergrad was in chemical engineering. I was interning at the start of this summer, and most of my work there was in electroplating. So I guess I'm here to take a deep dive into the course and learn more about what I was doing.
Right.
Hi, I'm Sahil, and I'm a second year master's student in material science and engineering as well. My research is mostly on hydrogen modeling and blending inside of metallic materials. I also took a a batteries class in my undergrad, and I went through that kind of made me interested in electrochemical processes and electrochemistry as well.
This is I'm first year master's student, and I come from the nice program. So I chose this class because I think I'm interested in the track. I'm down in Chile. I'm from the environmental engineering department. I'm interested in this class because I like to focus on natural treatments using electrochemistry to extract and materials from ground.
Hi, I'm Sean, I'm a fourth year undergrad in materials engineering. I kind of just like electrochemistry, redox reactions and batteries, so I thought this would be a fun class to take.
Okay.
I'm Josie, I'm a second year PhD student in CBE. I'm working with Dr. Nabi, and I'm interested in this class because my research is about conductive hydrogens. So I'd like to learn more about electrochemistry. Hello, my name is Val. I'm from chemical engineering, second year master student. I'm also in Navi lab. The reason why I want to take this class is I want to explore more about the industrial aspects of chemical engineering.
Hello everyone, my name is Larry. I'm a fourth year in undergrad chemical engineering. And the reason I took this class is because I was just interested in learning more about renewable energy. And I feel like it's really good.
Hello, my name is Sophia, and this is my first year as a master student in chemical engineering. And I took this class because it's a really important part in my research in processes. My name is Reagan Lee, and I'm the first year of master student, and I study in the applied of chemical science, and I'm interested in the electrochemical.
Hi, I'm Drew. I'm a second year master's student at the chemical engineering department, working with Professor Christophides. I'm taking this class because I'm just interested in electrochemical systems.
Hi, I'm Alex. I'm a first year master's student in chemical engineering, and I also
And I took this class because I'm interested in energy management. Hi, I'm Neva. I'm a fourth year undergraduate student in the chemical engineering major. I took the class to be kind of interesting and doing some conductor options, so I kind of just wanted about the class. I think this class was, I don't think we were gonna want to. So my friends did this class last year, so we have the reasons to talk about.
I'm Rami. I'm a fourth year undergrad in material science, and I'm taking this class because I did like analysis research and I want to.
I'm Alex. I'm a fourth year undergrad materials engineering major, and honestly don't know too much about like electrochemistry and stuff, so I just want to get a little show on it.
I'm Mason. I'm a fourth year materials undergrad, and I'm taking this class because I'm interested in fuel cells and flexible batteries. So,
I'm Kyle. I'm a fourth year materials student, and then also trying to get my master's. And then I want to work with batteries, so this is perfect.
I'm Jeff. I'm a third year chemistry student, and I was interested in taking this class because of economic protection as my internship.
Well, when I'm a fourth year engineer student in this class, growing interested in electrochemistry and renewable energy. My name is Ivy. I'm a fourth year undergrad chemical engineering student, and I'm taking this class because it sounds cool.
My name's Andrew. I'm a third year undergraduate chemical engineering student. I'm taking this class because it was generally interesting, and I'm really into batteries.
I'm taking this class because I want to.
My name is Jenny, and I'm the engineering contractor in this class.
I'm Tyler, the fourth year undergraduate chemical engineering career. Working with the field for some production research. I want to get more perspective on the topics.
I'm Lisa, I'm 7-year graduate student in chemical engineering. I'm here just because I'm interested in that.
I'm Stacy, I'm a 2nd-year master's student. I work with Professor Peterson, and my research is about chemical polymer, but I just want to explore more topics and.
My name is Ethan. I'm a first-year master's student studying green energy systems. I did my undergrad here in mechanical engineering, and I chose the program because no matter what you do, you're going to need energy, and it's going to need some clean.
Hi everyone, my name is Angela. I'm a 2nd-year PhD student in material science and engineering. I'm kind of just taking this class, I guess, a way to explore the different challenges.
Hi, everybody. My name is Aaron. I'm a first-year PhD student in materials science, and my research is focused on aqueous batteries. So it's good about this.
All right. Okay. All right. Good. So as you can see, we have people from chemical engineering, from material science, from chemistry, right? Some people with backgrounds in physics. So we will try to make the course as open to everybody as possible, right? The key is that you will learn the fundamentals of electrochemistry. I will show you the books that we will use, or the book that we will use. The lectures are 4 credits. We have 2 hours of lectures Monday and Wednesday from 2 to 4. One weekly section of revision, right? On Friday noon to 1 p.m. is here as well, or?
I think so now that we choose to should be.
Okay, so it should be here as well. I recommend that you come, particularly this Friday. So this Friday we will just do, we will review Laplace transform. We will go a little bit over the math. Okay, my office hours will be after the class from 4 to 5, not 4 to 6, 4 to 5. The grading. So you're split into the undergrads, right? If you cannot hear me, please sit down a little bit. I mean, let me know, but also maybe sit down a little bit closer. So the undergraduate students, right? So you will have 30% of your grade is the homework. You will have the midterm 30% and the final 40%. If you're a graduate student, the homeworks are both a little bit less, okay? And in addition, we have something that is a term paper. And in Brun Learn, there is also a document that talks about the term paper guidelines, okay? So eventually, we will go over that as well. You will work in groups of 3 or 4 students, okay? So graduate students. And then at the end, you will present a short paper, and then you will also do a presentation of 15 minutes, okay? All right. So for the term paper, again, this is only the graduate students. There is a document that is called Term Paper Guidelines in Brun Learn. There are a few deliverables, okay? What we want is to see a 1-page executive summary describing the topic, and you will upload it to Brun Learn by October 30th at 2 p.m. So what is this, right? So you will get in groups of 3 or 4 people, right? The 3 of you will write together 1-page summary, right? And then you will send it to you saying, we're interested in fuel cells, okay? Or we're interested in microbial fuel cells, or we're interested in batteries. We're interested in something, right? And use 1 page very quickly of why, okay? So essentially you will tell me what is the background, what is known, right? And what is it that you plan to do in the rest, like 1 month and a half more, or 1 month that you have, okay? Then you will have an oral presentation on December 4th or 6th, okay? This is the Wednesday or Friday of the week 10. And essentially what you will do is you simply present 15 minutes or so on the topic that you have selected, all right? Why do we have this executive summary? So that I can maybe give you some guidance. Maybe I can tell you, well, this is, maybe you can look at this from a different angle or something like that, all right? The idea of this presentation, right, is that you will let us see how is it that everything that we have learned during the class actually comes across in that presentation, all right? So you will present maybe a couple of papers. You will say they did these cyclic Bolt thermograms, right? This is the information that they read. We did a simulation. We extracted values from this paper or something like that, all right? The term paper then is due at the beginning of the final exam. So that will be week 11, right? And you will upload it in BroadLearn by the beginning of the time of the final exam, that's on Monday. All right, there are 2 textbooks. This is the main book that we will use. This is Electrochemical Methods. This is by Alan Bart and Larry Faulkner. The picture that you see here is from the 2nd edition. This is what the 3rd edition looks like, okay? Whether you use the 3rd edition or the 2nd edition should be fine, all right? For the most part in the homeworks, I will put most of the homeworks problems come from the problems in the book. So I will just tell you for the 2nd section what problems and what problems are in the 3rd edition, sorry. Okay, the software that we will use is MATLAB. Are you familiar with MATLAB? All right. Do you have access to MATLAB? Do you know that you have access for free at UCLA? All right. So please install it. All right. So Electrochemical Methods, this book, right, by Alan Bart, is very fundamental. All right. So it's easy to start with. Okay, but most of the problems are related maybe to small scale electrochemistry. Couple micrometers maybe or so, right? It is not relevant for industrial applications of electrochemistry, all right? There is this other book by John Newman, okay? This is called Electrochemical Systems. This book is much more useful, but it's a little bit more difficult to start from here, all right? So the idea is that we will start with the electrochemical methods, right? And then we will look maybe at a couple of papers. So you don't need necessarily to buy this 2nd book. If you want to buy one book, buy this one because this is more basic, more fundamental. All right. But if you're going to work in electrochemistry, you actually probably have to learn John Newman. All right. So we will introduce some of the concepts from John Newman from the Newman electrochemical systems as well. So this is what the 4th edition looks like. There is also a 3rd edition, 2nd edition. I don't know. There is a PDF file that I know that many people share of this book. So I think you can also use that, all right? So as it says, right, it's not mandatory. If I want you to read a chapter, most likely I would put it in BroadLearn, all right? But if you're interested in electrochemistry, I will definitely recommend that you buy that book as well. All right, you can actually read the 2 chapters, the first chapters of the 2 books and compare them, right? It will tell you can ignore the counter electrode. Just focus on the working electrode. This book will tell you that's not true, right? You actually have to look at the working electrode and the counter electrode as a whole, right? So this is more of an engineering view. This is more of a chemistry, if you want, a chemistry book. Yeah. All right. So this is the syllabus. That table is in the document that you have right now. Okay. So today we will have maybe so AV is Alan Bart and JN is John Newman. Okay. If it's in bold, that's what we actually will read. John Newman is just recommended. Okay. You don't need to buy the book. I don't want you to tell me that you had to buy the 2 books. Buy one, the Alan Bart. Okay. So we will have some introductions to electrochemistry. We will continue that on Wednesday. On Friday, okay, we will have a review of Laplace transform and the basics of electrochemistry. Who has learned Laplace transform? Who has not? So since I have been teaching this class, no one has complained about the math. Okay, so the math eventually will be fine. So math should not be a problem, even if you think that your background is not very strong in math. Later, I will give you this document, okay, and we'll discuss a little bit more about Laplace transform, what it is. But on Friday, we will go in detail, and we will do the exercise that are in this lesson. All right. So there you can see the different classes. When are the homeworks due? Okay, so we already have a homework one that I think is already available in Learn. Is due on, so sorry, I'm supposed to give it on Wednesday. Okay, so that's what it means. And this is when it's due. So it will be due Wednesday of next week. Okay, so you will have a week, typically with 10 days to solve the homework. All right, and then these dates with an asterisk mean that I will record that lecture because I'm not here. These are the weeks of AICHE. The AICHE meeting is in San Diego this year, so October 27th to October 31st. So I will as well upload those lectures. And there's a midterm. There's a midterm, all right. November 4th, and it covers Alan Barr's chapter 1 to 4. All right. All right. And then this is the second part, right? So we will cover chapter 9, chapter 10. We will look a little bit at basic concept of catalysis, batteries, active fuel cells. This year I will try to go a little bit faster, so maybe we can introduce some additional topics at the end. All right. And the term papers will be December 4 and 6. And the final is already in my UCLA, right? So the date is the Monday of the finals week. Okay. That's December 9th. All right. Any questions so far? I will try to record the lectures, but when I post them, I'm not sure, right? Maybe you will have them before the midterm, right? I would suggest that you just come in person, right? There will be a lot of writing in the blackboard, okay? So that might not appear in the recordings. So the first two lectures today and Wednesday is mostly slides based, but after that, I think it will be a lot of use writing and taking notes, okay? Any questions?
Are we gonna have a break during the lecture?
Yes, we will have 10 minutes, 10 minutes or 5 minutes of break. We will try to finish always at 3:50. Okay. All right. All right. Well, good. Okay, so today I want to cover three main aspects, right? Just as a sort of an introduction, right? I will try to convince you if you already don't know that energy is a precious good. I will talk a little bit about water and energy. What is that nexus? And then the water and energy and environment nexus. All right. So I always like to start with this figure just to calibrate a little bit the scales. All right. So you know these units of power, the watt. What is 1 watt? 1 joule per second. And joule is a unit of energy. All right. So 1 watt is a unit of power, right? All right. So I will put some different units here, right? So use for you guys as a reference point, we consume energy at a rate, like worldwide, we consume energy at a rate of 17, 18 terawatts. Okay, so that's 18 terajoules per second. Where do you think that this will land? Okay, what is the energy, the power consumption of a computer? Not during charging, but once you're actually, how much power does the screen in the processor consume? Range. Trying to get you guys a sense of energy, power.
I know that air dryers they will use is around like 2,000
2,000 kilowatts,
So-
right? That would be similar to the coffee maker.
Yes, yes.
Right.
So that would be, the laptop is lower than that.
It's lower, all right? So a laptop is typically 25 to 50 watts, okay? So it will be somewhere here in the watt scale, right? As you pointed out, right, a coffee maker, a typical home appliance, right? A hair dryer, a fridge consumes energy at a rate of 1 kilowatt. So how much power do you think that you need to keep a plane on the air? Equivalent of how many coffee makers? So this is the coffee maker while it's actually making coffee, right? How many coffee makers do you need or will be equivalent to a plane?
1,000
1,000, okay. So that would be a power consumption of
mega.
1 megawatt, right? What is the power output of a nuclear power plant? The scale.
Gigawatt.
A gigawatt, all right? So 500 megawatts to 1 gigawatt. Okay, so this is 3 orders of magnitude, right? So every time it's 1,000 times more, right? Okay, and so you can imagine, right, that our consumption is 18 terawatts, so around 18,000 nuclear reactors. And I think there is only like 500 or so, maybe less, right? Okay, so 18,000 nuclear reactors, big nuclear reactors. Okay. So here in the LA County, right, we have a little bit over 10 million people, okay? So then the question is, how much energy do we consume? So this is total energy consumption. This is stationary and mobile in 2017. Is that many terajoules in 1 year? Okay. Stationary means use the energy that you consume in a industry, right? Or in your home. Mobile is the energy that you consume in a car, right? So if you add everything together, that's how much terajoules we use in 1 year. If you were to put it in watts, okay, so 1 year, 365 days, 24 hours per day, 3,600 seconds per hour, right? It will be energy consumption of around 34 gigawatts. Okay, this is the power for 34 gigajoules per second. Okay, it's the equivalent of 34 nuclear reactors. We don't have how many nuclear power plants we have around LA.
0. No?
I think there is one operated by Edison, right? 1 or 2, but 2. But is that in San Diego?
Yeah,
Or-
one
One in San Diego.
One in San Diego. I don't know if it can cover. Sorry, it's not operational. Yeah. All right. So right. Okay. But this is used for you guys to get a sense of scale, right? So you can imagine it. LA County, 10 million people. We consume energy at a rate of around 34 gigawatts. Okay. 34 nuclear reactors. We don't consume only electricity, right? We consume gasoline, we consume different things, right? All right. So this is how the energy consumption has been increasing over the last 200 years. This is the global energy consumption, and in the blue line is the population, right? So this figure is just to show we have around 8 billion people. We consume energy at around 17 terawatts, right? And they trace each other. So what this means is more people, more energy consumption, right? We take energy from different sources. Okay, so initially from the 1800s, we used to use traditional biomass. We used to only burn things, right? Eventually, we found coal. Then we transitioned to or added crude oil. Then we started to extract a lot of natural gas. And then it's used in the last 60, 70 years that we started to use a lot more hydropower and solar energy and wind. Okay. But it's still more than 80% of our energy comes from fossil fuels. So how much energy do you think that you consume, or how much power is the average power consumption per person here in LA? So if one coffee maker is 1 kilowatt, right? If we take all the energy of LA and we divide it into 10 million people, how much energy is that? Essentially 34 gigawatts divided by 10 million people. Okay, so that is around 3.4 kilowatts. Okay, so while you're sitting here, you use for each one of you, we'll have plug in, right? 3 coffee makers, 3.5 coffee makers making coffee the whole time. Right? It's not only power, right? But if you look at what is the average world energy consumption, it's around 2 kilowatts, okay? So 2,000 watts per person. If you look at the average, obviously, in the US or North America or Western Europe, and you compare it with India and Africa, there is a little bit of a gap, all right? So this is the average in the US. LA, cities that are big, right, where the population is concentrated. Just because it's concentrated, we tend to use less energy per person, okay, in average. Okay, we can make use of energy a little bit more efficient. You can imagine that if you're in the Midwest, right, and you have to commute 50 miles every day. In LA, you will not commute 50, well, maybe. You will commute 50 miles because it's just too long, right, for the traffic. But in the Midwest, that's actually a typical distance to commute, right? But you can imagine that you're taking your car, all that mass with you, all right? So that actually consumes a lot of power. All right. And obviously, this also includes industry, all applications, right? Okay. So the challenge is that because 80% of our energy comes from fossil fuels, right? If you just look at the chemistry, if you have carbon, let's see if I can. You have carbon, right? You add oxygen, you generate CO2, and that's the way that we release energy, right? If you have oil or natural gas, you don't only generate CO2, you also generate water, okay? Why? Because somewhere the hydrogen atoms that are here in the hydrocarbons need to go somewhere, right? So we also generate water and we make energy, okay? And then this also generates some pollutants. So here, this figure on the right, what it shows you is the CO2 emissions in kilograms of CO2 per gigajoule of energy extracted, right? For different sources. And what you can see is that wood, all right, generates the most CO2 for the lowest amount of energy. Coal is next, crude oil, and methane is actually more efficient in terms of how much CO2 we generate per unit of energy. Why is that? Why do you think that we generate less CO2 from natural gas? What is the main component in natural gas? The main molecule is methane, right? So how is methane different from ethane? You have a single carbon-carbon bond, right? So methane has just a lot of carbon-hydrogen bonds. You can make those carbon-hydrogen bonds and make water and CO2, all right? And that is why per any hydrogen or carbon atom that you release, right, you're actually maximizing the amount of energy that you can release and minimizing the amount of CO2, okay? Why many power plants are moving to methane? Simply because it's just more efficient, it's much cleaner to burn. Why is methane cleaner? Not only the CO2 emission, but what other property does CO2 has, methane has compared to crude oil?
The gas.
It's a gas, right? So what happens when you have a gas instead of a liquid?
What's that?
Yeah, but you have to imagine that all these fossil fuels come from the degradation of biomass, right? So then the amount of impurities that you have are actually less because transition metals, for example, will not some of them come to the gas phase as carbonyls or whatnot, right? But for the most part, right, it's a gas. So it's already much cleaner than something that is like a liquid or a solid, right? Where you actually have a lot of contaminations in it, right? Yeah. All right. So before we had a figure that was the CO2, the energy consumption, right? This is actually the CO2 emissions that are linked to each one of those sources, right? So that's just taking the information on that table from gigajoules to amount of CO2 that you generate, right? And what you can see is that by and large, right, the burning of coal generates most of the CO2 emissions, then petroleum, and then natural gas. And then we also have cement production, okay? So actually, the making of concrete generates a lot of CO2. Where do we generate a lot of CO2 in concrete? In the composition, right? So you actually need to burn it, right? And remove the carbonates that are there, right? And that generates CO2 and the energy that you put into the process, right? So there's a lot of interest in reducing emissions associated with cement, gas flaring. Have you seen flares in oil, or if you drive up north, right, around Bakersfield, well, you see a lot of these wells with flame, right? Mm-hmm. So why do they burn the gas?
Transport.
Hard to transport, right? So a small amount of gases, right? You will not build an expensive pipeline just to move everything, right? Mm-hmm. So methane has a much stronger green house agent component. So it's per molecule, it will hit much more than CO2. right? So it's easier if you actually burn it, so you reduce the heating effect, right? Okay. But gas flaring, I think, also contributes with around 1% of the CO2 emissions. All right. So some of the very significant emitters of CO2 in the chemical industry are ammonia, right? Where do we use ammonia? What? Yeah,
Fertilizer.
for fertilizers, right? Okay. Ethylene propylene. Plastics, right? Yeah, right. So ammonia, I think, contributes with only ammonia contributes around with over 1% of the CO2 emissions. The same ethylene and propylene. Okay. Other emitters are methanol, because we produce a lot of methanol on large scale. Carbon black, chlorine, and caustic soda. How do we make chlorine and caustic soda? It's actually an electrochemical process, right? Where you take sodium chloride and then you do electrolysis. Right, so where is the CO2 there? All right, so most of the electricity generated by burning natural gas. Okay. The making of styrene as well. Yeah. All right, so then you pump more CO2 into the atmosphere. It has a greenhouse capacity, right? So if you don't reduce the amount of CO2 that you generate, right? You could end up in different of these type of scenarios. Okay. All right. So I always like to look at the global energy landscape, right? So I would like to see where are the sources of energy and where is it that we use them. Okay, so we actually use them in a few. We divided by sectors of our industry, right? So as the sources, you have crude oil, natural gas, coal, traditional biomass, modern renewables, and nuclear power. And the sectors are transportation, industry, residential and commercial, and electric power, all right? So you can see crude oil, right? We take oil and we make a lot of gasoline for transportation, right? We make jet fuels, we make normal gasoline, right? Some of those components in crude oil, we'll also use them for industry, right? To make chemicals like ethane, propane. Sometimes we make it from naphtha. Right? Then you have natural gas. Natural gas is mostly methane. You have some ethane, propane, right? Natural gas, we use a lot of it to make for industrial applications. Okay, so we make hydrogen, for example, from natural gas. We also use it for a lot of heating in residential and commercial, and we also use it to generate electricity. And coal has been used traditionally for the generation of electricity, but this is changing, right? So you can imagine that this is the levelized cost of electricity, right? So this is the levelized cost to generate electricity using fossil fuels. And when you see different alternatives, biomass, hydro, solar power, right? Actually, this is a little bit outdated. This is 2016. Solar power is actually now much cheaper. The same as wind. So, but essentially what this plot is telling you is that making electricity from renewables has become competitive with fossil fuels. Okay? And so you can imagine that maybe in a short period of time, right? Maybe you can actually replace coal, the generation of electricity from coal, just purely with renewables, the same with natural gas.
Yeah.
Right. Okay. But renewables have a little bit of a challenge, right? But have you seen this type of curves? So they call it a duck curve. I don't know if you can see the duck there. Can you see it? Right, but this is what some people call the duck curve because they just look at that yellow part that is the renewables. Okay? So this, what it's telling you is that you can imagine that depending on the hour of the day, right, from midnight to noon and everything, right, the composition of renewable power, this is purely power. This is only electricity, right? You can see that the contribution of renewables increases during the day, right? Why?
Sun.
Mostly solar, right? But wind, for the most part, actually, wind, I think it's better at night. I think, which I didn't know. I think it's actually different from solar. All right. So, what they have seen, right, is that in California, at least, what we see is that the spot price for electricity actually becomes negative, right? And this is simply because there are some times of the year, like during the spring particularly, right? But we actually generate more electricity than what the grid can take. And many times what we do is we send it to other states, Arizona, right? The peak in consumption is around 6 p.m., 6 p.m. So this is when everybody goes back home, you start cooking, some people go back and they connect to the electric vehicles, right? So that's where actually there is a peak in the consumption of electricity, right? Sorry. This is the peak in cost. This is the peak in demand, all right? So around this time, 7, 8 p.m. when you start watching TV, cooking and doing all these things, all right? So a lot of people that work in electrochemistry are trying to solve that problem of how do I store electricity, right? When I have excess of electricity, and how do I transform it back to electricity? If I make a fuel or something, how do I transform it back into electricity when I need it, right? Okay. So I will recommend that you go into the California Independent System Operator, net generation, and you can actually look data from more recent years. This is 2017, but that has changed a lot in the last couple of years, okay? This is just power, right? If you live in LA, right? This is actually the distribution of energy consumption of each one of you, all right? For the most part, people that live in LA consume gasoline, not only power. Maybe you live close to campus, right? Maybe you don't need to drive. But for the most part, people commute, right? You need to move goods. You need to distribute food to supermarkets, right? So all that requires a lot of gasoline. Power is electricity, and this is natural gas, not for power or cogeneration, but sometimes it's heating or some other industrial applications. All right. So in LA, we consume a lot of gasoline. All right. So let's imagine, right, that somehow we solve this problem. The electric power, right, is all made from electricity. All right. Maybe you can expand these renewables, right, not only to the generation of electricity, but also to support transportation, right, to the use of electric vehicles. But the challenge is that there still remains industry and residential and commercial heating. Okay. Why industry is a problem? Even if you have a lot of renewable electricity, what is the problem with the industrial requirements that we have for energy? Yeah, you need energy all the day, but let's say that you have plenty of renewables, you have plenty of batteries to store that electricity. Why do you still need something for industry? So not only power. Huh? Is that, let's say, if you look at the product of the industrial processes,
the
right?
raw material, you need carbon.
Right, so you need a lot of materials. So you need plastics or advanced materials, right? So the question is, where do we get them from, right? If right now we're taking most of those building blocks to make those materials from oil or natural gas, right? So we need carbon atoms, okay? All right. All right. So then a lot of the work in our lab is, at least in my lab, is to answer these questions, right? Can we use renewable energies to make fuels and chemicals for transportation or industry? Can we make it from renewable sources? Can we use clean hydrogen for transportation, right? In theory, if you have hydrogen, right, that is made from water electrolysis and all the electricity comes from renewables, in theory, you have zero amount of CO2 per energy, right? But the reality is that if you do this, the whole life cycle assessment of how is that you make the electrolysis and everything has actually a footprint of CO2. Right? So this is not entirely true right now. Okay. And we make renewable fuels and chemicals that fit directly with our energy infrastructure. All right. So we can say, yeah, you can electrify vehicles. Anyone has driven an electric vehicle? Have you tried to charge it? Can you charge it in your house? What about all the cars that park outside in LA? street parking. Imagine that if you need to put as many chargers as you have these coin park meters, right? That is the scale at which you actually need to distribute electric charging, at least in LA, at my point of view, right? It's difficult to actually have everybody use electric vehicles, all right? So the question is, can you continue to use combustion engine vehicles, right? But can you make the fuel renewable in a renewable manner? Can you take CO2 and hydrogen from an electrolyzer and make gasoline? So we know that we can do it. Right? There are Fischer-Tropsch processes. That's something that industrially we can do, right? The question is related to cost. Okay, what will be the cost? Okay? So when you look at it, what is the cost for you to generate the electricity? What is the cost to take that electricity and make maybe hydrogen, right? What will be the cost to react that hydrogen with that CO2 and make jet fuels or make gasoline, right? So as chemical engineers, we always look at what is the cost, okay? Many of you will be hired as chemical engineers to solve that question, right? Is it feasible? Is it viable? Should we spend 5, 10, 15 years trying to develop something? Will it ever make sense? And if it makes sense, what would be the conditions? All right. Right? So that's sort of the questions that we try to answer in the most difficult question, because there is not enough information, right? So for me, we know how to make solar panels, right? We can scale that production, right? We can generate a lot of energy generation, right? But how to store that energy is a little bit of a challenge. Okay. So we have this vision of a sustainable energy infrastructure, right? Where maybe you can take power from solar, wind, or biomass, right? You can take biogas, continue to run probably those power plants, take that CO2, and with that CO2 and electricity, maybe you can make methane, so synthetic natural gas. You can use make hydrogen. Maybe you can make directly chemicals or fuels. Maybe you can use that electricity to make heat, right, for different applications. And hopefully you can get any CO2 emissions that come from the in industry or chemicals, right? Capture it, right, using renewable energy, and then put it back. But this is a little bit of a dream of us or many people, all right? Then the question that I always ask the students is, what is the actual bottleneck, right? What is the bottleneck to the development of electrified catalytic technologies? Because if you identify for whatever you're working on, right, whatever is your research topic, if you can actually identify what is the bottleneck, that will also tell you what is the critical path, right, to further develop whatever technology you're doing, right? If what you're doing is not really the actual bottleneck, the probability that your contribution is very meaningful will be reduced, all right? So I think if you're doing research, right, you try to identify what is the actual bottleneck and push through that bottleneck, right? Because otherwise, everything else that you might be making is just might be not very relevant, right? And at least in electrocatalysis, depending who you ask, right, or electrochemistry, someone will tell you we don't have enough materials, or the materials that we use are very expensive. If you do a spectroscopy, you will say we just don't understand enough about the mechanism. So I will spend more time doing spectroscopy, right? I will spend my time doing new materials, or I will spend my time building reactors, right? So depending who you ask, you're in different research groups. So if you ask Gaurav, he will tell you, scale it up, right? I agree. I think that's the bottleneck for many of these technologies, right? So what is the critical bottleneck? Depends of who you ask, all right? The main challenge that we see is to develop a sustainable energy infrastructure is actually learning how to scale up electrified production systems. I don't know how familiar you're with fuel cell technology. There are many groups that work in fuel cells, and what they do is test catalysts in the lab, small scale, and just publish papers, all right? And just move to the next paper, the next material, right? But how many of those catalysts actually get to make it into a device is actually very limited, right? So I think that was fine 5, 10, 15 years ago. I think now the funding agencies are also shifting in actually asking people, where are everything that you have been promising, right? Everybody can make materials, everybody can write papers, right? But where are the actual solutions? Because the problems that we have are coming, right? So I think there is a little bit of, at least in my point of view, scale up is a little bit of the challenge. All right. Let me see how is my battery doing. I just have enough time. So let's take a break here. Let's take 8 minutes. So we are back at 3:05.